Okay, so maybe some of students have questions from the previous lecture. So don't you can ask, maybe you try to solve some exercises. You can ask me, or you can write to me in the chat and we will discuss it. Okay?
Okay.
So, today, if you have no questions for now, we will continue our investigation of Brownian motion. And today we will study a very important property of it, such as a Markov property. So we will consider a Brownian motion as a Markov process today. So what is the Markov property of a random process? So let x be some, so let x be some process, x from t, we consider a process with time on the real line, and random process. And Markov property tell us following. If we consider all our process, so I will write some trajectory of it. So this is x. And if I have some information about all process up to the time of moment s. So this is, I know about the process x. And now I am interested about the distribution of the process at the moment s plus t, for example. So I am interested in prediction of the process here. So, and I know this part I know. So all information about a process is known up to time s. So the Markov property tells us that the prediction will depends only on the moment s. So this is the last moment of time when we observed the process x. So the prediction, let me write it, prediction of process x at the point of time s plus t with known information about process, about values, all values for example, x from r where r less than s. So this prediction depends only on value x from s. So we not need to know all trajectories here, but we need to know only the distribution of the process at point s. So let us write, so we will write this informal description of Markov process precisely later. But for what is for Brownian motion? So for Brownian motion, we can describe property in a little bit different way. So how we can describe the Markov process, Markov property in another form. So I will write again, I will draw a picture of a Brownian motion. So I have some trajectory of a Brownian motion. And okay, I know this all information up to time s. And since I know this value, so this is my trajectory of Brownian motion, I know the value of b of s. And it turns out that and now we consider the future of the Brownian motion after time s. And it turns out that if we consider new axis, here new axis, then we will have the same Brownian motion with starting at point 0. So this is another description of Markov property. Yes, so we do not need to know all trajectory before time s. We only need to know the information at time s. So now I would like to give the precise theorem that will describe this property for Brownian motion. So let's formulate theorem and we will prove. So as before, let me write that we consider B is a standard Brownian, is a Brownian motion. And and let S be some moment of time greater than 0. Then, if we consider a new process B from t plus s minus b of s. So this means that I just start from this point b of s, and I continue all trajectory to the future. So here t is greater than 0. So this is a new process. And the theorem states that this process is again a Brownian motion, and it is independent on the past. So this independent of the process B from R, where R from the interval 0s. So this theorem states that that this trajectory does not depend on the past of the process B. So let us prove this theorem. So all we need to check that the new process, first, that this is a Brownian motion, and the second, the independence. So for the, let me denote a new process by y from t is equal from b from t plus s minus b from s. So recall our definition of the Brownian motion. On the previous lecture, we state the property in definition for process under which it is a Brownian motion. So what we should check that y is a Gaussian process. So this is the main property. Why is it so? This is so because B is a Brownian motion, and from this follows that this is a Gaussian process too. And you can recall the definition for Brownian for Gaussian process, and what we need to state is that for times t1, t2, and so on, tn, the random vector t1 and so on, y from tn is Gaussian, and we can rewrite it using the definition of process y. This is b from t1 plus s minus b from s, and so on, b from tn plus s minus b from s. And this is also a Gaussian vector, since we have that linear combination of Gaussian process, again a Gaussian value, or so this is Gaussian. So this is the main property we check. Now the next three properties that we should check, that this first, that y from 0 is equal to 0. So let me write that we have, by definition, this is obviously 0. So the next property is checked already. The next property that we have for Brownian motion, we give the definition in terms of Gaussian process. So we need to specify its expectation for each t, and we should check that it is equal to 0. So from definition of the process y, t plus s minus b from s, and using the linearity of expectation, this is 0 minus 0, so this is 0. So the expectation as well, such as we need. The next property is, and the last, is the covariance of process y at point t1 and y at t2 should be equal to minimum between t1 and t2. So to prove this, again, I write the expression for process y, and this is of this form, b from s and b from t1, t2 plus s minus b from s. Now, using the linearity of covariance, so okay, I will write it the first step, but it is an easy. So we just write covariance with each part minus covariance b from t1 plus s, comma bs, minus then covariance b from s, b from t2 plus s, and the last plus covariance last term ps, comma bs. So recall that we know the formula for covariance of initial Brownian motion, and it is minimum between arguments. So this is minimum from t1 plus s, t2 plus s. Okay, the next one I will write the answer, because minimum between t1 plus s and s is s, because t is greater than 0. So this is s. For the next term, again, since t2 is greater than 0, we have here minus another s. and here minimum S and S is S. So we have here what we can write already answer. So this is minimum between T1 and T2. Yes, we all this is subscribed, so and this S minus this S. So that's all. We check the last property that tells us that considered process Y is a Brownian motion. So the next state of the theorem, so this is the first, we prove that this is a Brownian motion. And the second statement of the theorem says that Y is independent, Y from T is independent of the process B from R. So this is again easy to see because why? Because we know that Brownian motion has independent increments, and Y, the process Y, is the increment of the process B by definition, and this is independent with all values with I will write this set. So with B from R for each R. Yes. So this is since Brownian motion B has independent increments. We proved this property on the previous lecture. Okay, so this proves our theorem. So we know such a property for a Brownian motion that it starts anew if we consider some new point of time. But to investigate the Brownian motion as a Markov process, we will give another description of a Markov process in terms of transition probabilities. So what is this? So we can imagine that Markov process is an analog of the property of dynamical systems. So let me recall that for deterministic dynamical systems, what do we have? For example, we have some differential equations. So this is d from dt that describes motion of some object. So, for example, this u is the position of the object at time t, and it is equal to some function from x from from u from xt, and this first argument is the starting point. So we know that we start from point x from R. Yes. So this is such a Cauchy problem. And what do we have here? So we can give a picture. For example, for all trajectories that starts from some points. Yes. And what is the main property of the system of solutions. So we have the solution u from xt. Yes. And what we know for such deterministic dynamical process? We know that we can, if we know the position of an object at time s, for example, we know that we are here. We can solve for the equation. We can solve a differential equation with starting point of this. So we have here u at point s. Yes, we know this, which started from point x, for example. So we know this position, and we can solve it as new stochastic differential equation gives new initial point. So, and we can solve it up to time s plus t. Yes. So we have such an uniqueness of trajectory, and I can write the value of position of an object that starts from point x at point s plus t in another way. So this is the same as I solve the system, but with the initial point u from xs, and I solve it on the time interval t. So I write here t. So this is the main property of dynamical systems, that we can solve it step by step. And now for the Markov process, we can get a probabilistic analog of this property. So as we said, the Markov process depends from the all past only through the value of the point of the last observed point. So this is the same as we have in the deterministic dynamical system. So now we are interested to find an analog of this property. So we have such a property that we can find value of point at time s plus t through the value of point at time s. So let us describe more precisely this property for Markov process. But first, we need to give some notation for the past of the process, for example, process X. How I can describe mathematically the information of the past of the process X. And now I give precise mathematical definition for such object. So let me write definition. So first I will denote by f indexed with t. This is the smallest sigma algebra that contains all sigma algebra generated by values of process X from S, where S belongs to interval 0 t. So this is the information about the process from the for time from 0 to t. So this is all information of all values. So let me write precisely. So this is smallest sigma field, such that x from S is ft measurable for each S from 0 t. So we collect all information about values of x from S. Okay, so this is the sigma field generated by a process X, and for the future, in my lecture, we will denote by this sigma algebras, the sigma algebra generated by a Brownian motion. So I will be interested in a Brownian motion. So please note that now I am considering sigma field generated by Brownian motion. Okay, so we will now also I will give some another definitions just for state the mathematical terminology. So we will say that a process, for example, x from t is adapted to the family ft t greater than 0 if for every t x from t is ft measurable. So this is a definition for adapted, and we will say that we have a filtration that the family of sigma fields is a filtration if it satisfies the next property, that if fs is a subset of sigma field ft for s less than t. So intuitively you can imagine that we have for smaller s we have less information in fs than in ft. So I will call this family a filtration. So for future in my lecture, I consider filtration that associated with a Brownian motion. So now let me give the definition of a Markov process that allows us to give the analog property of dynamical system, as I told before. So this is definition. So since we have to deal with random processes, here now instead of some deterministic solution, I will have the probabilistic distribution of all trajectories. So this is why we are working now with distributions of process. So this is definition of a Markov family, and I need to have a different starting points for my Markov processes. So I will denote the process X with two variables X and T. So this is the family of T and X from R. This is a family of random processes. And it is called Markov family with respect to filtration f t is greater than 0 if first we need to know that X from X is adapted with respect to filtration ft, and the following properties holds. And first, as I told, I will need the distribution of the process X. So I will denote by P with index T from X delta is the probability that the process that starts from X and its value at point T belongs to set delta. So here delta is a subset of R, is a Borel subset of R, and T greater than 0. And the first assumptions says that P T as function of X is a measurable function. So this means that that's Borel measurable function. Okay, so why do we need such assumption? We will substitute instead of initial point X, we will substitute the random value. So we need to be sure that this is a random value again. The next assumption that I say that this first argument X means that we start at point X at the time 0, so this probability is equal to 1 for each X from R. And the third property says the Markov property by itself. So if I have some points of time S and T, it isn't 0, I'm sorry, X from some point from a real line, and delta is a Borel subset of the real line, then this is the main property, that the probability of X from X S plus T belongs to delta. So I will consider conditional probability. I write condition with respect to sigma field up to so at moment S. And the Markov property says that this is the same as I substitute here in this transitional probability. I will substitute the last known point in this sigma field. So I need to substitute instead of initial point. Here, instead of x, I substitute value at time s. And such way. So this is the definition of Markov family. So let me give some terminology here. So we will call this function that depends on three arguments. So we have a moment of time, the starting point, and set delta. This is transitional kernel for the Markov family. Markov family. So if I want to prove that some process is a Markov process, I need to find such a transitional kernel and check the third property of definition. So, and this is all what I need to do. And also first, let us prove some properties for this transitional kernel. So the property this that we should have here, that first for fixed t greater than 0 and x in R, if I consider the function pt from x and from delta, so I consider such a function as a function from sets. So this is a probability measure. So this is easy to see from the definition of transitional kernel. Yes, we defined it as a probability that some random value belongs to set delta. So this is obviously a probability measure. This is very easy to see. Also, we know that this transitional kernel is such that for 0 time interval, we come from the point x to the set of 1 point x with probability 1. Yes, that means that the process starts from the point x. And the third property is a little bit harder to prove, but it is an analog, as I said, for flow property of dynamical system. So let me fix 2 points S and T and some point at the real line, and delta is a Borel subset of real line. So how I can find the value of transitional kernel at time s plus t from x to delta. So this means that we would like to find the probability that x, that the random process which started at point x belongs to subset delta at time s plus t. And as I said, we would like to split it to parts. So first, I will consider, so I start something here, and I am interested in that the process at point s plus t belongs to some set delta. And I will do it in 2 steps. I will consider that the process at point s belongs to something, yes, to something. And then from these points, it moves to the interval delta by time interval of length t. So this is length t. So this is why we have such a formula. So we need to take all possible values for transitional kernels that start from S, and it comes to all little such points here, dy, yes. And then from this, from the points y, I come to the set delta by time t. So this is such a analog of the property of deterministic dynamical system. But here we have many possibilities for trajectories to have the values at time s. Yes, so we need to take all these values and integrate all possibilities. So how we can check this property? This property follows from the third property of the definition of Markov process. So let me write it. So by definition of transitional kernel, this is just the probability that the process which starts at point s at time s plus t belongs to set delta. Now I will use such an properties of conditional expectation. Recall that the expectation of some random value is I can find as the expectation of conditional expectation of this value with respect to some sigma field G. So now I will use this property, and here I have what I know, that probability of some event A. This is just the expectation of indicator of this event A. So I use these properties. And I continue, I can write this probability as the expectation of conditional probabilities. So I write expectation of xs plus t belongs to delta with respect to sigma field S. And so this is the probability. And from the third property of the definition, I write the third property of definition of the Markov process, we know that this conditional probability we can write as the value of kernel at time t from the value x from x at time s belongs to delta. Yes, this is just the third property of definition. And now how I can find this expectation? We know the distribution of this random value, and the distribution of this random value just has the measure So I write this here. Oh, I'm sorry, here not belongs, just comma. So I write here, instead of this random value, I write y delta, and here I write the distribution of this random value, and it describes by transition probability PS from x du. Yes, so this is just the definition of our transitional curve. So that's all. So we get such a property for Markov process that we can get the distribution at time s plus t through such distributions on the intervals. Yes, if I want to have distribution at this point, I just need to know distributions on first interval up to time s, and then on the second interval from s to s plus t. So, okay. Now, what is about Brownian motion? Come back to Brownian motion. I want to find this transitional probability for Brownian motion, but as we have in the definition the Markov family, and it starts from arbitrary point. So I will denote now the Brownian motion from two arguments, x and t. And so I will use the same letter, but in our notation, this is just x plus standard Brownian motion that I considered in the first lecture. So what does it mean? That I have a standard Brownian motion b from t, but I shifted to some point x here. Yes, and now I have b from x t. So let us prove such a proposition. That b from x t t greater than 0, so such a family is a Markov family with respect to filtration f t. Let me recall that now I consider the sigma field here generated by Brownian process. So such filtration with respect to filtration and transitional probability, transitional kernels. Kernel is equal to what we have, pt from x delta is equal to 1 over square root 2 pi t. You can recognize here just the distribution of Gaussian process that with mean x and standard deviation t. So this is for t strictly greater than 0, and for t equal to 0, we have just that p0 from x delta. It is just the indicator that x belongs to delta. Okay, so what we should prove in this proposition? So first, property in the definition of Markov process that p t as function of x is a Borel measurable function. And this is easy because we have such a formula. It's obvious because we have strictly, we have precise formula for P. The next property is obviously too. What we have that x, that probability that b from x comma 0 is equal to x with probability 1, also obvious because our Brownian motion starts from 0 and shifted starts from x with probability 1. And now we should check the third property, and it is a little bit harder. So what we should check from the definition of Markov family, we need to prove that probability that now we have Brownian motion that starts at point x belongs to some delta, conditional probability with respect to fs. This is the transitional kernel at time t from x comma s and delta here. So we prove here that the distribution depends on the past information only through the value of last observable value. Okay, so to prove this, what do we know for Brownian motion? We can work with increments of Brownian motion because it has independent increments, yes, so it's easy. So let us first consider such a probability that probability that b from x comma s belongs to some set A, and b from x comma s plus t minus b from x s belongs to some set B, for example. And I consider conditional probability here. So as we know, this first part is that this is measurable with respect to sigma field, and the second is independent of the sigma field. So I can write this event before the probability. I will write it as indicator of set A from the value b from x as here, and the probability of value that are the probability of the event that does not depend of sigma field, it just the probability, unconditional probability. B from x belongs to this. So this is unconditional probability. And I can write it, I know this distribution, yes, x. And I write here the distribution, so this is 1, 2p t here minus y squared 2t dy. Okay. Now I can generalize this formula for arbitrary. So let S be subset of R2. And I would like now to prove the analog of this property, but analog of this formula, but for arbitrary x from S, comma, b from x s plus t minus b from x comma s. So this is two-dimensional vectors belongs to S. So from the first, what is this? We find that this the probability find for S is equal to A times B, yes, if I have rectangular. But to give here the answer, let me denote by S with index at X. This is those Y from R such that the points X, Y belongs to S. So on the picture, you can imagine this as in the following way. We have X, Y, we have some set S, and what is this here? We fix here X, and I consider all Y's that belongs such that the pairs belongs to this subset. So this is a projection of the set at point S. So now I can continue this equality in such way that this will be, oh, I'm sorry, please correct here. Of course, I need to find conditional probability. I'm sorry. So I find here conditional probability, and it can be shown that this is equal to integral with respect to S, and I can take the this projection at random point of B from X S at point S, E from Y to the square 2 T Y. You can check that we show this formula, so we already checked it. I will write we checked it for S equal to rectangle. S equal to rectangle A by B. So please do it by yourself. It is not hard. You just need to write precisely what we have here for this S subindexed with X. And now how I can prove the main property that I need. I will take, now consider set S of the form. I take all values that such that X plus Y belongs to delta. So then the probability that Brownian motion that starts from X plus T belongs to delta under conditional of Fs. This is just the probability that I have B from X comma S such a two-dimensional vector S plus T minus B from X S belongs to S. Yes, this is just by definition of set S. Okay, and now I have that property that I proved, and now this S with okay, and now we have that this is equal to 1 to square root 2 pt integral S from B from X comma S e to the power y to the square 2 du. And this is equal. You can just to write this this set with indexed of bx from S, and this is equal. We just make change of variable. This is e to the power integral with respect to set delta, and here y minus b from x s to the square to t, oh, I'm sorry, I forgot here, t dy. So this is just in our notation. This is transitional kernel at time t from the value from b from x s, comma, delta. So this is what we need. So, okay, now we have such a transitional kernel, and it is good in the following sense. Let us consider some properties of Brownian transitional kernels. First, note that in case of Brownian motion, our transitional kernel has density. So we say that transitional kernel has density if we can write this value as integral. Here I will write small p t from x, y, dy. And Brownian transitional probability, transitional kernel has density. We can write it p from x, y. So this is just Gaussian density with variance t and mean x divided by. And now I would like to say a few words with connection to heat equation with the Brownian motion. So let us recall that we considered Brownian motion as a model of random motion of molecules. So we have seen that the random motion of molecules forces the microscopic motion of a particle. So now this gives us an intuition that a Brownian motion can transform, can describe the transport of heat in a media. So what we can write here precisely. Let U from Tx will be the temperature of some of a rod at position x at time t. So I give a picture. I have some rod, and for example, I have here some power, and heat moves by this rod. And I measure the temperature at point x here at time t. So I have two-dimensional process. And you are familiar with equations that describe this temperature. So it is known that Fourier heat equation describes the evolution of the temperature in the following way. So this function u satisfies partial differential equation. dt is equal to 1 over 2. And here the second partial derivative with respect to variable x. So initially, when this equation was written, it was not known how to solve it. But now, when we have the description of a Brownian motion, and we can imagine that the temperature is moved by a particle, yes, if they have here small particles of the media and they moved, and this can be described by a Brownian motion. And indeed, this is true, and I give you such an exercises that if I take the transitional density for Brownian motion, so let me fix here x, I will fix it. Okay, I will fix here y. So I have such a transitional kernel, transitional density minus x2 divided by 2t. And you can check just computing first derivative with respect to t and second derivative with respect to axis, that it satisfies heat equation. So I have now that transitional probability, the transitional density, this is small p, density 0 is equal 1 over half to x2 pt of x 0. So this is not hard to check, but when we solve heat equation, usually we have some initial distribution of heat on the boundary. For example, at time t equal to 0, we know that we have some function that we have some, let me write here, time t here, t, and here at position x. I have some distribution, initial distribution of heat here. So I have some initial value distribution. So assume that at point 0x, we have some function phi from x, for example. And how we can solve then this equation with such initial condition. And again, I have that t positive tx. I consider this equation again, but with initial condition. How I can solve it? So we need to specify the initial condition for distribution of a Brownian motion at time t. So this is another exercise. Please check if I have some function phi that is twice differentiable and is bounded. Then the solution to this heat equation I can get as follows. This is just expectation of value of this value phi here that I have here from Brownian motion that starts at x at time t. So exercise is to check that such a function u solves system. I will denote by star the system star. So this is the way how we can solve problem for a theory of partial differential equation using Brownian motion. So this is connection between the probability theory and a theory of partial differential equations. And here we use the so-called Markov property of a Brownian motion. Here I would like to stop for today's lecture, and maybe you have some questions about materials that we discussed today. So if you have no questions for now, again, I will send to you lecture notes, and you can find there some additional exercises, and you can write to me and send me your solutions or your questions. Please, you are welcome. It will be very good for you if you will try to solve some exercises, and we will discuss it on lectures, or you can write to me. So that's all for today, and thank you.